Okay, so it's 2 o'clock. So today I want us to take 10 minutes at the beginning of class to fill in the. You should have got an email about the teaching evaluation for this class. So use 10 minutes to fill that in. I mean, the department and I take it seriously, so there's not many questions. Fill it in, and I'll come back in 10 minutes. All right. And anyone who comes in later, just tell them what's going on. All right. Thanks. Okay, so thanks for that. Uh, we will quickly finish off this smoking data set, and then we will do the summary as usual. Then we'll do one more. I think it was helpful last time to have the summary done first, then do another example. So we'll do exactly that. But we'll finish this one first. If you remember this data set, there was one group that did a lot of it. It's basically trying to look at a data set that tries to use various variables to predict a person's lung volume. And some of those variables were like the age of the person, whether that person is a smoker or not, and there were others as well. So the data are not here, all right? The data are in this R code because it was long and I could not fit it. Google Sheets didn't like it, so I couldn't put it there. So just make sure you have the data. It's in the MATH219 R code document. And what I want you to do now is basically something like what we did for the house price data set. I'll just show you just above. Make a listing like this, and you can contribute to all the. I'll create a page where you can put the model that you fit, and then just report the AIC, the R square. There's no point putting R square, right? This was to teach the reason R square is useless. You can leave out R square, but you can report AIC and R squared adjusted, and what model did you fit. So that way we can all collaborate. So here's what I'm going to do. I will add a new tab here called smoking, and we'll just do exactly this. Here's the model, and you know when I say model, basically you can just put the after the tilde sign all the terms. You don't have to do anything else. Even with all the plus, it's okay. So in other words, just do something like what we have done before. So we'll just report AIC and R square adjusted. All right. So so basically something that looks like this. All right. So we'll have everyone contribute whatever model they can think of, throw some really simple ones and some really complicated ones with even interaction that involves three factors like A star, B star, C, and see whether it's beneficial making an ultra complicated model. So I don't know whether you realize that this is actually in some way how you should be doing your project, right? Because basically what is this course all about is trying to find a good model. All right, so I'll have you do that, and please contribute to the smoking one. So I'll start off by putting model 1. All right, model 1 was what we did together, and that was here. So model 1 is a linear model that just looks at age and smoking status. Okay, so I will start off just doing this. The first model had just age, plus S factor smoker, right? That's it. The AIC was, oh, it's right here. Okay. All right, so just a few more. Maybe we'll end with like maybe 5 or 6, and then we'll just quickly talk about it. But that's all I want. All right. Oh, also, today I will be opening up a homework. This will be the last homework, and I'm going to make it due like next Thursday. All right? It's a slightly longer, not very much longer, slightly longer because I'm putting together a few chapters worth, but it will be a good thing for helping you revise. It will be covering everything up to this point, basically. Just not the last chapter. The last chapter we will not have homework, but we will continue to do classwork like this. All right, so just giving you a heads up. Also, before I forget, for the project presentation, I know it's not in the rubric, but can I have every member of the group help present? So it's not like I collected the data, I did the analysis, I present. That's kind of not what the ethos of what a project should be. There, everyone should be involved in like as many aspects as possible. I know it's impossible to exactly demarcate who did what, but it shouldn't be one person doing one task only, and the presentation is one of those. I would like every member of every group to present, and the whole thing should take no more than, what did I say, 7 minutes or something like that. All right. We will leave part B first. The model 2 part we will do a bit later. Let's just do this part first. All right. The basically consider linear models which potentially use all available. So that's the one that we are doing right now. See, you can already see that you have found a model that is substantially better. The AIC dropped by a lot, R-square adjusted rose by a lot. Now you notice I'm saying a lot. I cannot give you a p-value. AIC, R-square adjusted, there's no statistical test. It is, you can't back it up with a p-value, but you can see that the increment has jumped a lot, all right, like that. Great, this is a good find. Your AIC went down, R-square adjusted went slightly up. Good. Let's actually, it's kind of interesting. Let's see how good, who can find a model that can top the top one right now. This could actually potentially be a game show, right? No one would watch because it's too nerdy, but game shows have to be like lowest common denominator. It has to be, there is nothing to understand. Wheel of Fortune, turn tiles around, you know, that kind of thing. So But this is so like a game show, like competing, like who can come up with a model which has even the lowest AIC and the highest R-squared adjusted. I don't even know what's the best possible one. I've never really investigated, so I'm actually interested to see how low can you go and how high can you go. This is something I didn't teach the class. Let me talk about this. This is a shortcut, and I think you all have discovered it. To do what? I want all the individual terms. I also want all the two-factor interactions, three-factor interactions for. But I didn't want to do this because I didn't want to encourage you to throw the what's the expression I want? Throw everything at a problem. But this is a shortcut way to have a model which has everything you can think of inside, plus interactions and all that kind of thing. All right, just a couple more minutes, then we'll start. I just want to see if someone can beat the 8051. But I don't, this is pretty high. I think in the history of this problem, I've not seen any better than that. But I might be wrong, but just a couple more minutes. See if anyone can think of anything, because it doesn't mean that having a model with everything is necessarily the best thing. That's what makes this problem very intriguing. Right? You can drop a variable, but have some interaction that may do a little bit better, but I don't know. Right? So I know some of you may be asking, is there an automated way to do this? Yes, there are people that have worked out, but you know that you can go check out yourself if you want. Of course, there's a systematic way to, there's only a finite number of combinations of variables, so you can actually write something that could do that for you. This was very interesting. So let me talk about this one. Oh no, don't delete. Okay, yes. Yes. Now, if you look at the formula, right? Do you see an age over height? That's quite clever actually. Who's to stop you from actually creating? Do you know what you have just done? This is called feature engineering. To use a data science-y word, a lot of people call now explanatory variables features. So you are generating an explanatory variable, you're making a new one. Age over height didn't exist as an explanatory variable. It's perfectly okay to make your own explanatory variable. That may actually help. So this is actually called feature engineering. They've just done that, which is a legit move. You can do that. All right. So I'm gonna call it closed. It seems this is the best one. So I will from now on keep a historical tab and see if anyone can beat the 617. It's pretty good, this one. All right? Okay. So
we're looking for the lowest AIC.
You want the lowest AIC and the highest R-squared adjusted. That's right. Okay. They tend to corroborate, right? They don't tend to contradict each other. Sometimes they do, but it's pretty rare. Usually they go in the same direction. I mean, they not the same direction. They lead you to the same conclusion. Okay, let's go on to something more concrete. Let's finish this part. Fit model 2. Model 2 is model 1, but it allows for an interaction between smoking status and age. All right? Model 2 is like model 1 was what? So model 1 had just Smoking status, you can see, smoking status and age. This one adds just one thing, which is smoking status star age. All right. So fit that one. You can actually save time. Make an ANOVA table skeleton like this. It's already on our class record. Modify it to include a smoker age interaction. A lot of the work has already been done. You can use this framework. Just modify that table. What happens when you include a smoker age interaction? All right. And then you can start reporting the prediction equation and predicting things and all that. All right. All right. So this is done already. So I'm going to try to. Oh. This, okay, that's very 805, great. Oh no, that's the one we were talking about. Okay, so this is this is, okay, 8054, okay, good, all right, yeah, very good. So, so it does seem, in this case, that we are rewarded. I will paste this later onto the class record, all right, just for completeness. It just seemed that we are rewarded for a very complicated model in this case. So the complication is worth it. That's what we're saying, all right? It's not always true. In this smoking data set, it was worth it having super complicated model, all right? Okay, the same group that did the first one has already done the second one. So let's take a look. All right. Model 2 allows for an interaction when you have a smoking status and age interaction. What's the rule we learned? All quantitative variables have df of 1. We are going to revise that in the summary sheet, but every quantitative variable has df 1. Of course, 1 times 1 is 1. So all that happened was your total doesn't change. That's always n minus 1. Your resid just dropped by 1. I mean, this is academic. It's not a huge difference, but it's just whether you know how to make the correct ANOVA table. Very good. Fit model 2 in R. Is there evidence of an interaction? What do you want to do? Go check the ANOVA table, and you can quote the p-value for the interaction term. What is the reference distribution? I think we have done this easily 50 times, I think. You go with the df for interaction and the df for the resid. So 1, 6, 50. Report the prediction equation. What's the code for getting a prediction equation? We have not done this a lot. We have done ANOVA a lot. What's the code for getting prediction equations? You go to summary. Very good. You ask for summary. But as I said, don't use the tests, the p-values in the summary, right? Use the ANOVA table one. Volume hat equals intercept, smoking status, age, and smoker age. Good. Use the prediction equation to predict the lung volume of a smoker aged 50. I won't go into the work for this. What happened here? You want a smoker, so that person's smoker score will be 1. Smokers are labeled 1 for smoking status. The person is age 50, and then you do the same thing here. Smoker 1, age 50. It's as simple as that. And you'll get more practice with this in the homework, right? Where you physically use, well, not physically, you actually use the prediction equation like in the algebra class. Use the prediction to predict, prediction equation to predict the lung volume of a non-smoker, now aged 50, or also age 50. Can you see the contrast? Can you tell why this was so severe? Is it intuitive? Look at the prediction equation. First of all, it's very strange. It seemed, and I want to point this out, it seemed as though smoking gives you a higher lung volume, correct? Isn't this a plus sign? That's strange, but that's just a bump up that the model gave you because it was trying to fit the model. That stays the same. Every smoker has this bump up. But do you see something? That's why the importance of an interaction term. This is where you get knocked for being a smoker. The older you get, the effect of smoking keeps on, it's a gift that keeps on giving, I say. Every year you are older, the fact that you're a smoker, you keep losing lung volume as you age, which means the effects of smoking get more and more severe the older you are, and it's cumulative. I've not focused a lot in this class about interpreting coefficients because I don't want that to be the focus, but if someone asks you, can you tell me what this number means? Can you say something like what I've just said? You see, it's very telling. It means while this has a plus sign, this is actually a model fitting adjustment. The way the model was fit resulted in this. This is counterintuitive, yes. But you must mention to your client that this does not change again for anyone once you are a smoker. This is a fixed effect. But every year you get older, the fact that you smoke, you keep losing, and it's not a fixed amount. It gets more and more every year you age. So this is a very nice interpretation of what you're saying, all right? Okay, write down the theoretical model equation. So you know what I'm going to do? I'll help you out. We can take this one from here and modify it. Theoretical equations, right? What are we going to do? So you have some alpha smoker, beta age, and then, okay, so you have now you have a smoker and age thing. So what you need to do actually is say something like there's a gamma now times alpha. We don't use alpha anymore. Sorry. This would be the smoker variable times age, something like that. All right. This just means whatever your smoking status is, that's a variable. It's 0 or 1. That gets tacked on to your age with a star. This is also a Greek letter. It's another. I know this one. That's why I gave you the answer. We didn't formally write this down because I am not going to focus on this on the exam and all that. I'm not going to ask you right because I don't want this class to be all about writing models. There's some model notation you need, but when it gets really technical, I'm not. But you understand? So if you take your smoking status, you star with your age. That's what you're doing, and you put dump another Greek letter in front of you, something not used yet, so gamma or something like that. Calculate ACI for the theoretical coefficient of age. So can we use the ideas that we have found from the previous one? Oh, let me get out of this. So when we did the previous one, we want a CI for the theoretical coefficient of age. So you know what I'm going to do? I'm going to copy this and ask you, what do you need to modify here? Is this still true? Estimate, some T thing, and SE of estimate, isn't it still true? But can you update this part, right? Is it T651 or is it T something else? What should it be changed to? And because this is another model, you'll find that the estimate also does change. The model has been refit already. This model has an interaction term. So the age estimate, the coefficient of age, that estimate has also changed slightly. So you can go refer to your summary statement for model 2 and just update this one. All right?
I have a question
yes.
about these equations.
Yes.
If you go back to model 1,
okay.
You can see that the slope for the smoker is negative.
Yes.
Right? Which would make sense because the normally would go down if you are a smoker. Not.
That's right.
How come it's positive?
Yeah, it's because it was trying to accommodate the interaction term. The interaction term, you can think of it, was so powerful, it was taking away your lung volume so quickly that so the model kind of like settles on its own what happens. But that's right, it would have been easier to interpret if the coefficient for smoker had also been negative, but sometimes that doesn't happen. And that's why I told you when you interpret, we have to be very, very careful, because some people will question you that, oh, that means it's advantageous to be a smoker. You must say, that's because it was trying to adjust for an interaction term that keeps taking negative 0.16 points away from your lung volume the older you get. Very good question. That's why before you declare some model for someone, you have to really look very, very carefully at answer. Okay, so this one is T650. Did this change? I think, or am I sitting in that? Thank you. This did change as well as SEs change as well. So the whole point is these things change. Model to model, these things. This was a severe change because this one turned negative, you know. Right. In other words, what is it saying? The estimate for lung volume, lung volume, does it decrease with age? Yes. It does. Whereas the previous model, it actually goes up with age. So you might say, again, why do they contradict? Because when you put more things into a model, you are using different estimations, and so the model is trying to settle itself. What's the best fit, basically? All right. AIC, is this model slightly better? Is model 2 slightly better? Let's see. So model 2, 5922 versus 57, yeah, marginally, 1114 dropped to a yes. All right. So thank you very much. This was helpful. I hope this kind of thing is at least interesting to the class. This class is very deadpan. Well, not all the time. So I don't know how you're respond. To me, these things are what I would want to get from an applied statistics course. You want to know how to use it, right? Not really into the math, but we do get into some math. You can't avoid it. But I try to minimize it as much as possible. Okay, thank you. So this was good. So let's do the summary sheet. And we'll see, this is a much shorter one. See what you can do with this. Then we will discuss. If we can't finish, we'll continue on Wednesday. All right?
Thank you.
This is just one side. Let's do. All right? Yeah. This is fantastic. Behind the scenes, this model has been someone found. Wow. Okay. See, by using logs and yeah, they're very good. That's exactly what you should be doing in real life when you're being asked to model something. Very good. And it's open-ended. You could do better. That's why it's very tantalizing, actually. Can you do better and better and better and better? It's the sky's the limit. Well, what are you going to do, right? So, very good. I am going to import this to our page. All right.
Is the AIC actually?
Yes, it's still true. All right. Even if AIC turns negative, but AIC can be negative. I believe it can because it's a log likelihood, all right? But it's still smaller is better, all right? Okay, I just want to do a few. We'll see how many we can go. Let's answer. Strangely, I'm going to ask you to do this one first. In R, if the levels of the fixed factor were called A, B, C to I, because I did say there were I levels, which level will not be represented when you look at the summary statement for the prediction equation? Does anyone know the answer to this? What's the convention that's used in R? A. Good. A. Why? Because A is the first, right? A is not represented. And what that tells you is, if someone is A, then you zero out the others. That's what it means. All right? Good. So now, write down the statistical notation for an ANCOVA model. So this one you go with YK equals, and the first thing is always some kind of generic intercept term. Right? And I want to take the sigma term away because I want you to appreciate what you're writing. I'm going to just go write the long way. Alpha 2 times Z2K. All right? Okay, why? Because Z2 will take the value 1 if you are at level, oh no, I just said, oi, what am I doing? I just said A, B, C, right? I'm going to call this not alpha 2, but alpha B. And call this ZB. I want you to see, I want to avoid having numbers. I think it's clearer to use letters. If you are a B person, then your ZB value will be 1. Your ZB score is 1, and you would get the alpha B. Can you tell me the next term I'm going to write? Plus? Alpha something else. So alpha C times ZC for the kth person. So why is there this K thing? This is because it depends. If person K is a B person, then that person's ZB score is 1. That person's ZC score is 0. It depends on the person, all right? And of course, you go on and on until the last term, which will be alpha what? We try to stick to alpha. What is the final level? I. Good. Alpha I, ZI, K, like that. And then finally, we have our explanatory variable x. And this one, you can put it as beta times x. Right, like that. You want to be very careful. You can put xk, but I think it's pretty obvious. It's that the value of x for that person, and then plus epsilon. Good. All right, let's quickly do that. I think we might be able to finish this. Okay, what's the source of variability? Of course, the first one is the fixed factor. How many levels does it have? Capital I, therefore the df is I less 1. Good. The next one is the quantitative variable. Quantitative variables have df, always 1. And then the next is unexplained. And then you have total. And what's the total df? Always? Yes. And this one, please don't bother. Subtraction. All right? If there are interactions, the df of the interaction term is always the, starts with P, product. Product, which product of the df's. All right? Good. Give the f-stat ratio that can be used to test for significant, what do you use? MS what? Yes, the MS of the fixed factor. That's right. Divided by, as usual, yes. What's the reference distribution? F. In this case, I less 1 and the, yes, good. Give the f-stat ratio that can be used to test for the utility of the lone quantitative variable. Can I change this? It is ms not of the fixed factor, but ms of the x, quantitative variable, quant variable. And what's the reference distribution? Not an fi minus 1, but a, yes, f1. Very good. You see how quickly we're finishing this? Excellent. Last thing, how do you construct a confidence interval for the theoretical coefficient of x in the model? You always use estimate plus minus t, and what's the df? Yes. Times what? Standard error of the estimate. Yes. Finally, when comparing models using R-squared adjusted, what is better? Smaller, bigger, what? Good. Bigger is better. And that's not how you spell bigger. Right? When comparing models using AIC, smaller is better. Both R-squared adjusted and AIC are balancing historical what? Okay, this is a short word, fit. They are balancing historical fit and future prediction accuracy. All right, so this is something you need to know. A model that fits really, really well fits what well? It fits historical data well because you fed it, and some people call historical data training data. This is all about data center training. Training data is historical data. It's what you can see. So it can fit historical things well, but a model that is ultra flexible begins to have very poor predictive power for future things as not seen. Last one, the better the historical fit, the higher what statistic gets. We don't use this statistic very much. Very good. Not R-squared adjusted. R-squared adjusted has been adjusted. R-squared keeps getting better and better the better it is, but the worse AIC and R-squared adjusted begin to get. Yes. All right. Thank you. Okay, that's all for today. I will see you all on Wednesday. Please check your email. There will be a homework opening, but it's due next Thursday. All right.